So I want to make sure, in the interest of full disclosure, I've seen the question, but I promise I haven't had a lot of time to think about that question. So what I do as a demo in the next 20 minutes is as a genuine demo as I can make it. And I will say it's a short amount of time, even for me who have written these questions and know everything there is to know. And even though I will explain some of my steps, in some places I might have to kind of skip some of the explanations to go fast enough to try to do this within 20 minutes. Even me, if I waste too much time explaining, I'll run out of time. So when you do the attempt, please make sure you use these 20 minutes to make sure you can put together an answer that you will put it in the answer box. You can always organize your work later after the time limit runs out. There's no real time limit to it other than, these rules still apply when you are organizing your work. Don't get outside help while you are organizing your attached work. So with that, let me start. And I don't know if I remember what question it is. So I just verified that it wasn't one of the questions I've done. But I don't think I remember it now. Yes, I don't think I do. Oh, this one, yeah. So with this one, really the main thing I want you to do is direct integration. It was one of your homework questions, and I know many of you can do it by superposition. I don't want that. I want you to do it by direct integration. Now, if you are trying to use a superposition to answer it, this is how you would do it. Just add I total is 1/3 of mass of this thing, which should be 7/3 m times the length of the thing, L/3 squared, plus 1/3. That's the rotation inertia of the left piece. Now the rotation inertia of the right piece would be 1/3 times 7 is the mass, so 7 times 2, 14 over 3 times m times now 2L/3 squared. So yeah, you can definitely do it that way, get a correct answer that way, simplify it. But what I'm looking for is not that, but a kind of step-by-step process doing the integration. So for that, this is how you should set it up. I've done this illustration many times, but let me do this for the purpose of this particular demo. So just this is going to be my center of rotation. I won't change anything. So this would be where my x is set equal to 0. That way I can just use 1x for two different purposes as my coordinate variable that I'll use for integration and as the distance from my center of rotation. And the first thing I think about when I look at a question like this is a representative element. I can imagine dividing up this rod into many tiny little pieces. This representative element, it has some distance x, or it has some coordinate x measured from this reference point. It has some certain amount of mass dm, infinitesimal amount of mass dm, and then it has some side, infinitesimal size dx. And even though for the entire rod, I don't know what its rotation inertia is, it's too complicated. But for this representative mass, I can say, I can write down its infinitesimal contribution to rotational inertia. It's going to be basically 1 for the point mass, which is the amount of mass times the distance. This is where I'm dual using x, both to mean my coordinate and my distance squared for the distance from the axis of rotation. And in order to get the total rotational inertia, what I do is, integrate this over the rod, which means I'm adding up all these infinitesimal contributions. So this is schematically what you will do, and the rest of the steps is basically figuring out all the details of how to work this out. So I first need to work out dm. This infinitesimal amount of mass, I need to write it in terms of x so that I can actually do the integral. So here the main idea is, this amount of mass that's here, that I think I can work it out from a kind of a proportion to the total mass. So as a proportion to the total mass, which I guess in this question, let's make that 7m. That's what the question gave us. Total mass is 7m. And this proportion, intuitively, I'm thinking, the whole thing has length L. and this has a portion of length dx. So I think the total amount of mass in this piece will be this ratio times the total mass. By the way, I'm going this circuitous route rather than using the idea of density, because the way we do topic order in this class, we haven't covered the density technically yet, but I think this kind of ratio is something that people can intuit their way through. So that's what I'm doing. So let me write that out, and that might be actually all I need. Let's see, I'm still integrating over the rod, and I have, let me just promise to write dx at the very end. I have a 7m over L, that is actually the density, times I have x squared, and I have times dx. And this dx is my variable of integration. And this x is my coordinate variable because I'm dual using x for that purpose. So far I've been saying I'm going to integrate over the rod. It's a kind of schematic representation. Let me make it concrete. It's going to go from x equals, this endpoint, minus L over 3, to x equals 2L over 3. And I think if I somehow swap this order, it should still be fine. Or maybe not. I don't know. Sign errors are some of those things where, if you get a negative answer for total rotation inertia, you made a sign error, so fix it. Like, it doesn't matter how you got the sign error, just fix it. All right, so I think this is an easily doable integral. It's a polynomial integral. I remember the antiderivatives are here. The antiderivative is 1/3 x cubed. And I can check it by imagining taking derivative of this. And I take derivative, 3 comes down, it becomes x squared, I get that back. So that's my antiderivative. With that knowledge in mind, I do the rest, factor out the coefficient, constant coefficient, 7m over L. And my antiderivative is the indefinite integral, 1/3 x to the third power. And I evaluated the limits from minus L over 3 to 12 over 3 to make it definite integral. So when I do that, I get, let me factor out 1/3. So 7 over 3 m over L times the upper limit. So that will be, I'm just going to do the cube in my head. 8 over 23 L cubed minus this. 2 minus cancel out. So it's going to be plus 1 over 23 L cubed. I can simplify this a little bit. This is going to be 9 over 27, or 1/3 L to the third power. 1 factor of L cancels. So doing all that simplification, mostly in my head, 7 over 9 and L, oops, not that, M, and then L on the numerator squared. Good. Let's double check by simplifying this expression. So before I wrote, so let's see. Combining these two, it's so far 7 over 9, and then combining this 81. So that times ml squared, and then ml squared. Let's imagine factoring it out, or so it's plus 14 over 3, so it's a 14 over 9, and then I guess that, so okay, 2, so it's 4 times that, so 56 over 81 times ml squared. So combining these two, it's 63 over 81. 9 fits into both of them, so 7 here, 9 here, times ml squared. Yep, that's the answer. Also into direct integration work attached. All right, how much time? I don't think I have a lot of time. 11 minutes? Oh, okay, I have enough time. So, all right, that's rotation inertia. Yeah. The rod will swing if released from, what is the angular omega of the rod when it reaches a vertical orientation as it swings. Yeah, so there's two parts that you need to think through. So it's a conservation of energy question. So conceptually, it's not too hard. You are going from this setup So this is snapshot 1 to snapshot 2, where it'll be vertically oriented. And conceptually, it's not hard in that you say, okay, I think energy is conserved. So you say conservation of total energy, mechanical energy. So you say total energy in snapshot 1 is equal to total energy in snapshot 2. Let me say my y is equal to 0 here at the pivot point. That makes certain things simple. So my total initial energy is actually 0. 0 gravitational potential energy, 0 kinetic energy. And in snapshot 2, I will have gravitational potential energy plus the kinetic energy, and my gravitational potential energy will be negative. And this is the part where you do have to be a little bit careful. The pivot point will remain at the same point. The kind of the displacement you care about is this displacement of the center of mass. And one kind of simplification is this distance is 1/3 L, and with the uniform rod, this will be 1/2 L. So this particular distance here, this is one of the fraction differences I have memorized. That should be 1/6 L, or you can do 1/2 minus 1/3 and work out that. So that will be how much the height changes. So here it should be minus mg times 1/6 L. That plus 1/2. Let me say just I total. This is the rotation inertia from part A times omega squared. So if I just want to make it really easy for myself, I can say omega is, solving for it, just doing the algebra in my head. It should be mg L over 6 I total square rooted. And since I did the algebra in my head, let me just do dimensional analysis to make sure the units come out right. So the units are square root of kilogram times meter per second squared times meter divided by rotational inertia as unit of kilogram times meter squared. Kilograms cancel, these cancel. 1/second square rooted, so 1/second. That's correct unit, so that's probably correct answer. So I'll say omega is equal to square root of m times g times L. Oh, and this m really should be 7, the total mass of the thing. Now, if I had plugged this in, that part would have canceled out, but maybe I make a mistake elsewhere. 7 GL divided by 6 times I total, where I total is from above. 3, 4 steps. All right. Do I have enough time for challenger part? 7 minutes. I think I might. Because I think didn't I give myself center of mass? Maybe not. Yeah, I don't think I did. All right. So let me try to do this part more quickly. I'll copy this over to save myself a little bit of time in drawing. So actually, some of it actually being given the density, it simplifies some things. Actually, so for challenge part C, where I had this ratio stuff before, this will now simply become the linear mass density lambda of x times dx. Like out expression, oops, not dx. Expression wise, it's simple. You don't have to think through those ratios, just density times length. And I'm given lambda x. So let's work out the I. Now, this is the part where you do have to just do the integral. There's no possible way you can reason your way through this with the superposition principle. That really what this. So what I'm integrating should be lambda of x, that's 28 m over L fourth times x to the third power. That's dn, except for dx. I have dx over here. Times, I still have x squared from the expression for the infinitesimal rotation inertia. So this is going to be x to the fifth power, meaning this antiderivative here will give me 1/6 x to the sixth. It's still reasonably easy integral. I used to give like polynomial functions, and that took way too much time, so I started doing that. I can do that. All right, so factor out all the constant coefficients. 28 m over, and let me factor out 6 over 6 L to the fourth power times, I have now as the integration x to the sixth power evaluated from minus L over 3 to 12 over 3. So that's going to be uh, 28 m over 6 to the L to the fourth power times, I'm going to factor out the L to the sixth power, L to the sixth power, and then the rest is 2 to the sixth power. I don't think I have that memorized. Over 3 to 6th power minus, and then minus or plus 1 to the 6th power is 1. I do have that memorized. So now the nice cancellations, I get L squared as expected. And let's see, 3 to the 6th power. Do I know that? How much time do I have? Just to type it out. So I'll just say I total is equal to 20 over 6 times 2 to the 6th power plus 1 divided by 3 to the 6th power times m L squared. It's not as simplified as I would prefer, but hey, it contains all the necessary information. If anybody's interested in the simplified version, they can do it themselves with enough time, or put it into calculator once they can do fractions maybe. So that's C first part, and for part B I do the same thing. So this is the same snapshot that we are considering. The only thing that's changing is I think my center of mass changes. So I need to work out where my center of mass is. That's the biggest thing that will take a lot of time here, because basically, this distance will remain the same, but instead of this being this should now become this distance to x of center of mass. And that's why it's a challenging part. I don't focus at all in lectures on the formulas for center of mass. I'll write it down, and if only to demonstrate that I have it memorized. So the center of mass is defined this way. It's a weight or mass weighted average of position. So if I'm doing it as a sum, it would be you average the positions, but you weight it by weight or mass. So mi over sum of mi. Or for a continuously distributed thing, it'll look like 1 over the total mass. So here it would be m total times integral of all space of the density. That's the mass portion. Or the mass portion becomes, this becomes dm, which is density times dx. So I still have this x here. So it's going to be density times x times dx. Do I have enough time to work this out? 1.5 minutes. Am I having enough time to write out the expression? So m total, I don't know what I made that to be. So in the most general case, this is what you have to do. Integral of x going from 0 to L. Sorry, not 0 to L. No, distance from the left hand of the rod. So I think, yeah. So, oh, wait. I made a mistake. So I made a mistake here because I used the meaning of x as a coordinate thing. This integral should have been really, so what the correct thing would have been 0 to L here. So that's going to change that answer here. Oops, use the wrong limit. And here, let me just, I don't know if I have me to finish the whole thing. I'll just write out the expression that once integrated will be correct. So for the numerator here, this is the density, x to the third here, and then x, so x to the fourth power times, yeah, I knew I was gonna run out of time. Let me just finish writing it out, and I'll at least show you the solution. So that's the numerator. That divided by m total, you just have to do this integral. X is equal to 0 to L, 28 m over L to the fourth power, the density. There's x to the third power. And then just the dx without the x. That gives you this integral will give you the total mass. And I think when you do that, you get 7m. So I guess I set it so that your m total will still be the same. Challenging part, I think the reason they stay in the question is because I like those. I don't want to get rid of them entirely. But I do think within 20 minutes, you're not expected to have enough time to finish this. So it's fine if you don't finish it. Don't worry about it. So I'll just label these for C. I'll say C, second part. I'll paste in my work, and then I'll show you the solution, at least to make sure that of what I have written down, that there are no mistakes. So let's at least do that much. And I do have to end the session and go. I got a meeting in like 20 minutes. Yeah, this question is one of those, calculating things by direct integration. It's not a thing that's so important for this class. Like if, as you are reading through calculating rotation inertia by direct integration, if all of that seemed like really complicated and you don't want to deal with it, for the purpose of this class, it's fine. It doesn't really matter. But I want you to make sure that I have at least one question or one homework questions, one place where you are required to do it is it's the kind of skill that will become more important later on in higher level classes. So when you get to physics 4B, there are certain questions in electrostatics and actually magnetostatics also, where the best way to get an answer is by direct integration, by setting up the integral and just chugging through it. And if you've never done these calculating things by direct integration, then that's a lot to handle in one semester. And I want you to kind of see an approach to it, detailed approach in this semester, so that when you see it again in physics 4B, that it'll feel more familiar. Now, a lot of physics 4B, we will come up with the techniques to avoid doing those direct integrals. That's what Gauss's law and Ampere's law are about, applications of them. But still, it's a technique that, again, at the higher you go, where you have to, like in engineering, there's something called a finite element analysis. That's basically a numerical version of what you do here. And the better you understand the concepts that's used in setting this up, the more you will understand the fundamental things like finite element analysis. That's bread and butter of a lot of civil and mechanical engineering. So anyway, so I've attached the work. Let me save work and continue. And I think of where we are right now, I can't I'll show you answer here. Let me bring in my instructor view, and we will make sure that I didn't make any serious mistakes. That I haven't corrected already. Almost there. Almost there for test this time to work. Here it is. Okay, so So I'm checking 7, 9. If that's correct, then should be correct. That is the solution, but there shouldn't be any mistake because the answer is correct. Here, omega is, I don't know if the solution has it in the same form. 7mg over 6 over I total. 7mg, yeah, well, yeah, 7mg L over 6. Oh, did I forget that? Did I say 6 there? Oh, I think I copied it wrong. That should have been 3. Yeah, so in my head, I did a 2 canceling out a factor of 2 here, and then I forgot about it. There's a factor of 2 mistake there. This 6 should be 3, or I should have a 2 in the numerator. Oops. um, I'll note that in the edit. And with that, I think with that correction, the rest of it, this is correct. And when you plug this in, you get that. I don't know if this is generally something that will be useful. For part C, so I think no, even this would have been wrong. So without using wrong limits, let me see if I can rework what the correct algebraic answer there should be. So if I evaluate it from, then actually a lot of these factors become easier. So basically this 2 to the 6th power, this just becomes 1. So it should be 14 over 3 ml squared. So I total is equal to 14 over 3 ml squared. That's what it ought to be. Let's check. Oh, so I just made it harder for myself. What? Oh, yeah. This is still wrong. This is uh, this is about end point. So yeah, so challenge part again. I think I made a ton of mistakes. So let me do this. I might just edit out the challenge part entirely and just have the edit go directly to here. So that's the challenge thing here. There's mistakes that I've acknowledged, and in fixing the wrong limit, this is what I would have to do. So before I was using x in 2 different meanings. I was using x to mean the distance and the variable of integration. So um, so in this challenge part where I'm given an expression where x is defined in the question, left hand of the rod, I can no longer use it as my expression for distance. So what I would have to change is that here this x squared part, I would have to rewrite it to mean, okay, distance from this point of rotation, I have to write it as, let's see, I think x minus L over 3. Then when x is equal to 0, it's minus L over 3, but you're going to be squaring, so minus part doesn't matter. And then when x is equal to L over 3, it'll be 0. And when x equals to L, it'll be 2L over 3. Yeah. So I have to use this over here. Now it's going to be squared, and so it's basically the expression that you are integrating here. That's going to look like x to the 3rd power from the density expression times x minus L over 3 squared. And working that out, again, I think I do have the correct, so scrolling down through the answer solution here, that's x center of mass, which I kind of set up the expression. Let's just look at that after. Setting up rotation inertial calculation, all that. Yeah, you need to do that, do that, do that, and you have basically this to set up, x to the 3rd. and then that thing squared, and then now from here on it's complicated. So I think for the solution, I just set up a Sage method expression where if you click evaluate, it'll evaluate. Because some of the numbers are randomly generated, and doing it this way is easier. Yeah, so that's one. And let's double check the center of mass calculation. So yeah, this is the definition of center of mass, which I was pointing out. So you would have to do all this calculation, and yeah, denominator, I set it up so that it'll give me 7m. Okay, for the numerator, you would need to work out this. Yeah, so, and I guess when you work that out, it would have been 4/5 L, and that would give you this 4/5 distance. So the difference would be something that's not 1/6. So what would it be? 5, I think 1/15, maybe. No, sorry, not 7/15, maybe. So for the omega calculation, you work out that distance, and yeah. So I don't think I bother with any of that. Just set up the equation. Same equation, just it's more complicated, and just have once you are able to set up the equation, have Sage method. It's easier. So challenging part, I would do, it's a good exercise for you. When you have plenty of time, don't sweat about doing it within 20-minute time limit. It really wasn't meant to be done that way. Well, you've seen me not be able to do it correctly within the 20 minutes after doing A and B. And I think even if I didn't waste the time by explaining, I still wouldn't have be able to do this part within 20 minutes. And you so may make a ton of mistakes. It's the kind of thing that you think through it thoroughly. It's a challenging question, so do it as an exercise outside of 20 minutes. Don't worry about getting it right within 20 minutes. And you have these answers to double check after you finished it to see how much of it you did it correctly the first time around.